At 4 seconds past 20 past 1 in the afternoon, on the 23rd of March 2005, a cloud of hydrocarbon vapor drifting across an oil refinery in Texas City found something hot enough to ignite it. 15 people were killed, 180 were injured, 43,000 residents were told to stay indoors. Houses were damaged 3/4 of a mile away. 2 years later, the United States Chemical Safety and Hazard Investigation Board published its findings. The report runs to more than 300 pages, and the first thing it does, before any diagram or any timeline, is warn you against the way you are probably about to think about it. Because there is a version of this story where somebody left a valve closed. That version is true. It is also, according to the investigators, the least useful thing you could take away. This is what they found instead. The Texas City Refinery was, at the time, the third largest oil refinery in the United States. Before 1999, it was owned by Amoco. In 1999, BP merged with Amoco, and BP subsequently took over running the plant. A refinery of that size is not one machine. It is dozens of process units, each doing one chemical job, connected by pipes. The unit at the center of this story is called an isomerization unit, usually shortened to ISOM. Its job is to take certain straight-chain hydrocarbons and rearrange them into branched ones, which have a higher octane rating and are more useful for blending into gasoline. Feeding that unit is a distillation tower called the raffinate splitter. If you have ever seen a photograph of a refinery, you have seen a distillation tower. They are the tall vertical columns. Inside, a liquid mixture is heated at the bottom. The lighter components boil off and rise. The heavier components stay low and are drawn off near the base. A tower separates a mixture into parts by exploiting the fact that different molecules boil at different temperatures. The raffinate splitter took raffinate, a mixture of mostly straight-chain hydrocarbons, and split it into a light fraction and a heavy fraction. It was 170 feet tall, standing outdoors, full of flammable liquid. And on the morning of the 23rd of March, it was being started up. That word matters more than it sounds. A refinery unit that is running steadily is, in a sense, the easy case. Everything is in balance. What goes in comes out. Startup is different. Startup is the transition from empty and cold to full and hot. And during it, nothing is yet in balance. The industry knew this. In 1996, Amoco analyzed 15 years of its own operating data and concluded that incidents during startups were 10 times more likely than during normal operations. BP's own process safety guidelines said that startup and shutdown were two of the most critical periods of plant operation and recommended that supplementary assistance be provided. Experienced supervisors, operating specialists, or technically trained personnel. Hold on to that recommendation, it comes back. To run a distillation tower safely, you need to know how much liquid is in it. Too little and the pumps at the bottom run dry. Too much and the liquid climbs into the pipework at the top, which is designed for vapor, not for a column of liquid. So the raffinate splitter had a level instrument. And here is the fact that makes everything that follows comprehensible. The tower was 170 feet tall. The level transmitter measured across a span of 5 feet, located within the bottom 9 feet. Not the bottom 9 feet as a first stage of a wider system. That was the system. Above 9 feet, in a 170-foot tower, there was no level measurement at all. In normal operation, the tower ran with a few feet of liquid in the base, and the instrument covered exactly that range. The instrument was designed to answer the question the operators normally needed answered. It was not designed to answer the question they needed answered that morning. the investigators' own view was that this was not enough. They wrote that redundant instrumentation extending above the range of the primary level instruments is valuable for detecting excessive liquid levels. Now, how does an instrument like that actually work? It does not see the liquid, it weighs it. Hanging down inside the base of the tower is a heavy metal rod, and the instrument does one thing only. It measures how much that rod weighs. Drop the rod into liquid, and it gets lighter, because the liquid pushes up on it. The deeper the liquid, the more of the rod is submerged, the more the liquid pushes up, and the less the rod weighs. Read the weight, and you can work back to the height of the liquid. Everything in that depends on knowing how hard the liquid pushes, and that depends on how heavy the liquid is. The instrument on the raffinate splitter was set up for a fluid with a specific gravity of 0.8, 8/10 the density of water. But hydrocarbons expand as they get hotter, and a hotter, lighter liquid pushes up less. So consider what happens as the tower fills and the furnace fires. The liquid rises past 9 feet. The rod is now completely submerged. It should simply read full and stay there. But the liquid is also getting hotter and lighter than the fluid the instrument was set up to expect. Lighter liquid, less push. The rod weighs more, and the instrument faithfully converts more weight into a smaller number. The reading did not stick at the top. It came down. At 9:51 that morning, the transmitter read 97%. At 11:16, it read 93%. At 12:42, 80%. At 4 minutes past 1 in the afternoon, it read 78%, which the control system displayed as 7.9 feet of liquid in the tower. The actual level at that moment was 158 feet. The tower was very nearly full, and the only instrument watching it was showing a level that was low and falling. Not frozen, not obviously broken, falling, reassuring. There were meant to be backstops. There was a redundant high-level alarm, a separate hardwired switch, independent of the transmitter, set to sound at 7.9 feet. It did not activate. There was a sight glass, a window that lets an operator walk up and look at the liquid directly. It had been reported as unreadable, coated on the inside with dark residue, and had been non-functional for several years. And on the 22nd of March, the day before, a supervisor told instrument technicians to stop checking the critical alarms because the unit was starting up and there was not enough time to complete the checks. The startup began at 2:15 in the morning. The night lead operator began filling the tower with raffinate feed. At 3:09, the high-level alarm sounded, at a level of 7.6 feet. That was expected. Filling continued until the transmitter read 99%, which should have meant just under 9 feet of liquid. The actual level was 13.3 feet. The instrument was already understating. Filling the bottom of the tower until the transmitter read 99% was not unusual. The investigators found that most ISOM startups had experienced high liquid levels in the splitter tower. It was, on the board's evidence, a common practice rather than an aberration. At 5 in the morning, the night lead operator left the refinery, a little over an hour before his scheduled shift end. The dayboard operator arrived at 6 minutes past 6. The nightboard operator left at 23 minutes past 6. The investigators found that supervisors and operators poorly communicated critical information about the startup during the shift turnover, and that BP had no shift turnover communication requirement for its operations staff at all. At 7:15, the shift supervisor arrived. At 47 minutes past 10, he left the refinery because of a family emergency. No supervisor and no technically trained person replaced him. Recall the guideline from the previous chapter, the one recommending supplementary assistance during startup. A staffing assessment had specifically recommended an additional board operator for all ISOM startups. None was assigned. Meanwhile, feed continued to enter the tower, and nothing was leaving it. The startup procedure required the level control valve at the base of the tower to be used to send liquid onward to storage. That valve was closed. Liquid went in for more than 3 hours and none came out. Why would anyone do that? Because from inside the control room, the picture did not add up to an overfilling tower. The board operator had a screen showing raffinate leaving the unit, but the investigators found that the display did not give adequate information about the imbalance between what was flowing in and what was flowing out. The one number that would have made the situation obvious was not presented in a way that made it obvious. The furnace was lit at 5 minutes to 10. 2 more burners at 16 minutes past 11. More fuel at 10 to 12. Each of those increases pushed the liquid higher through thermal expansion and boiling, and each of them made the liquid lighter, which pushed the instrument reading further down. By 10 to 12, the actual level was 98 feet. By 22 minutes to 1, it was 140 feet. The transmitter read 80%. The investigators also examined the people. The ISOM operators had been working 12-hour shifts for 29 or more consecutive days. The report concludes they were likely fatigued. The central training department had been reduced from 28 staff to 8. Simulators, which would have let operators practice exactly this kind of abnormal situation, were not available to them. The procedures themselves, the report found, were outdated and did not address the operational problems that recurred at every startup, which had taught operators over time that procedures could be altered or did not strictly have to be followed. None of that is an excuse offered by the investigators. It is a description of the conditions under which a person was asked to notice something that no instrument in front of them was reporting. At 4 minutes past 1, the tower held 158 feet of liquid, and the screen said 7.9. At the top of a distillation tower, there is an overhead line. Its job is to carry vapor away to be condensed. On the raffinate splitter, that line ran from the top of the tower down the outside of it to 3 pressure relief valves located 148 feet below. Pressure relief valves are the last line of defense in a pressurized system. If pressure rises past a set point, they open and they dump the contents somewhere safer than a rupturing vessel. They are supposed to be the thing that saves you. At 14 minutes past 1, the liquid in the tower reached the top and began pouring into that overhead line. And now the geometry does something that is worth pausing on, because it is the part engineers find most elegant and most horrible. A pipe that descends 148 feet, filling with liquid from the top, becomes a column of liquid 148 feet high. That column has weight, and weight in a fluid is pressure at the bottom. The relief valves did not open because someone had overpressurized the tower with vapor. They opened because a tall pipe filled up with liquid, and the liquid's own weight pushed on them. Pressure at the valves rose from about 21 pounds per square inch to about 64. All 3 opened. They stayed open for 6 minutes. What came out of them was not vapor. It was a large quantity of flammable liquid, and it went where the disposal system sent it, into a vessel called a blowdown drum. The blowdown drum was a vertical vessel 10 feet across and 27 feet tall, fitted with a stack that discharged to the open air well over 100 feet above the ground. It had been installed in the 1950s. Together, the drum and its stack held about 22,800 gallons. It was never connected to a flare. A flare system is the alternative design. It has a vessel sized to safely catch the liquid, and a burner that combusts the remaining vapor. It is the safer arrangement, and the board said so. The Texas City blowdown drum instead vented straight up into the atmosphere. The report's word for that design is antiquated and unsafe. The investigators found the drum was simply too small for the volume the relief valves delivered. It filled. The liquid rose into the stack, and then it came out of the top of the stack in what the report describes as a geyser. The drum had a high-level alarm of its own. It did not sound. The float inside it was later found corroded with a hole in it. That last detail matters for a reason that is easy to miss. When the pressure spiked, the board operator began troubleshooting, and he noticed that the blowdown drum alarm had not sounded. He concluded that liquid was not going to the drum, and continued acting on the theory that the problem was a buildup of non-combustible gas in the tower. Volatile liquid, thrown into the air above a refinery, evaporates as it falls. It formed a flammable vapor cloud at ground level. The Chemical Safety Board determined that the most likely ignition source was backfire from an idling diesel pickup truck, parked about 25 feet from the blowdown drum. The report says most likely. It does not say certainly, and neither will we. The explosion followed at 4 seconds past 20 past 1. Every one of the 15 people who died that day was a contractor, and every one of them was in or around a temporary office trailer. Those trailers had been placed there by BP. The closest was 121 feet from the blowdown drum. Trailers, how large maintenance work gets done. A turnaround brings hundreds of extra people onto a site for a few weeks, and they need somewhere to keep paperwork, hold meetings, and eat lunch. So portable buildings get towed in, and they get placed where there is space, which tends to mean close to the unit being worked on. The question of how close is too close is a facility siting question, and at the time, the industry's reference for it was a document called American Petroleum Institute Recommended Practice 752 on the management of hazards associated with the location of process plant buildings. The Chemical Safety Board examined it and found something specific. Recommended Practice 752 provided no minimum safe distances from hazardous areas for trailers used in refineries. It set out a framework for companies to assess siting themselves, and it allowed a great deal of latitude in how they did so. BP's own workbook for the assessment generally followed that recommended practice, with some differences, including in the assumptions used about how many people a given blast overpressure would kill. The investigators also found that BP Texas City managers did not effectively implement their own pre-startup safety review policy, which was supposed to ensure that non-essential personnel were removed from areas in and around process units during startup. At 1:45 that afternoon, roughly 25 people were attending a safety meeting in the main control room. The startup was underway. 50 trailers and other portable buildings were later examined for blast damage. This is the part of the story where the distinction the investigators kept insisting on becomes concrete. The tower overfilled because of an instrument and a procedure. The explosion happened because of a 1950s disposal design, but every one of the 15 who died was in or beside a trailer, and those trailers had been sited as close as 121 feet from the blowdown drum by different people at a different time for reasons that had nothing to do with distillation. Here is what makes the Texas City report difficult reading, and it has nothing to do with the 23rd of March. Between 1994 and 2004, there were 8 serious releases of flammable material from that same ISOM blowdown stack. 8. Only 2 of them were investigated as safety incidents, and the tower overfilling was not novel either. The investigators found that most ISOM startups experienced high liquid levels in the splitter tower, and that neither Amoco nor BP investigated these events. Appendix 1 of the report is a table of historical data from 19 previous raffinate unit startups. The blowdown system itself had been formally identified as a problem 3 separate times. In 1992, 13 years before the explosion, the Occupational Safety and Health Administration cited a similar blowdown drum and stack at the refinery as unsafe. The citation was withdrawn as part of a settlement agreement after Amoco argued that the atmospheric stack design was consistent with industry standards. The drum was not connected to a flare. In 1997, a major modification replaced the ISOM blowdown drum and stack with similar equipment. Amoco's own safety standards required that blowdown stacks be replaced with equipment such as a flare when major modifications were made. It was not connected to a flare. In 2002, BP engineers proposed connecting the ISOM blowdown system to a flare. A less expensive option was chosen. Around all of this sits the financial picture the board describes. Cost-cutting and a failure to invest during the 1990s, first by Amoco and then by BP, left the refinery vulnerable. BP targeted budget cuts of 25% in 1999 and another 25% in 2005, at a time when much of the refinery's infrastructure and process equipment were in disrepair. Operator training and staffing were reduced. The board's finding is stated plainly: cost-cutting, failure to invest, and production pressures from BP Group executive managers impaired process safety performance at Texas City. That is the investigators' conclusion, not ours. There is one more warning worth naming because of how specific it is. The board found that important safety lessons from a British government investigation into incidents at BP's refinery at Grangemouth in Scotland were not incorporated at Texas City, and there is a number that recontextualizes everything above. In the 30 years before 2005, 23 people had died at the Texas City refinery. The board's assessment of how the organization responded to all of this, across numerous surveys, studies, and audits that had identified deep-seated safety problems, was that the response of BP managers at all levels was typically, in the report's words, too little, too late. Which brings us back to the warning at the start. The Chemical Safety Board investigated Texas City using the model of the Columbia Accident Investigation Board, the inquiry into the loss of the space shuttle. It quotes that board directly, and the passage is the key to the whole document. The Columbia Board observed that many accident investigations make the same mistake in defining causes. They identify the widget that broke, then locate the person most closely connected to it. The engineer who miscalculated, the operator who missed a signal, the supervisor who did not listen. And when causal chains stop at technical flaws and individual failures, the responses are equally limited. Fix the widget, retrain the person. Which leads, in that board's words, to a misguided and potentially disastrous belief that the underlying problem has been solved. So it is worth saying clearly what the Texas City report did not conclude. It did not conclude that this disaster was caused by an operator who left a valve closed. There is a second idea in the report that has traveled even further. BP measured safety at Texas City substantially by its personal injury rate, the count of recorded injuries per 100 workers. That rate was low. It was, the board found, a misleading indicator of process safety performance. Those are two different things. Personal safety is whether people trip, fall, or cut themselves. Process safety is whether the plant releases its contents. A site can be excellent at the first and failing at the second. The board's finding was that reliance on the low personal injury rate at Texas City failed to give a true picture of process safety performance. Texas City had a low injury rate and a 1950s blowdown drum discharging to the sky. Some of what followed can be traced directly to the board's recommendations. The rest belongs to a wider pattern the board was one voice in. In September 2005, OSHA fined BP over $21 million for 301 egregious willful violations. At that point, the largest fine in the agency's 35-year history. In January 2007, an independent panel chaired by former Secretary of State James Baker, convened at the Chemical Safety Board's urgent recommendation, reported that significant process safety issues existed at all 5 of BP's United States refineries, not just Texas City. That same year, the American Petroleum Institute issued Recommended Practice 753 on the location of process plant portable buildings in response to the board's urgent recommendation about trailer siting. It is the document the industry now points to when it decides where a trailer may and may not go. In June 2007, OSHA launched its Petroleum Refinery Process Safety Management National Emphasis Program, a program of detailed refinery inspections. And in April 2010, the American Petroleum Institute published Recommended Practice 754 on process safety performance indicators for the refining and petrochemical industries, responding to the board's recommendation that the industry create measures that actually track process safety, separately from injury rates. That standard is where the leading and lagging distinction was written down for this industry. BP sold the refinery to Marathon Petroleum in February 2013. The reason this case is worth your attention is not the size of the explosion. It is that almost nothing about it was hidden. The instrument had been reported. The sight glass had been unreadable for years. The blowdown stack had been cited by a regulator, flagged by an internal standard, and proposed for replacement by the company's own engineers. 8 releases had already come out of it. High liquid levels in the splitter tower had occurred on most previous startups, and neither Amoco nor BP had investigated them. The information was all there. What was missing was a system that treated any of it as a warning.